Hi, I'm Phil Norval and this short video is about energy use in industrial motors. I'm going to give you an introduction to how industrial motors work and some ways to improve their performance to reduce energy costs and cut carbon emissions. There are very few businesses that don't use industrial motors for one reason or another. They can be very obvious in places like factories where mechanical processes are central to the business's main function. But even office buildings will use industrial motors for things like driving ventilation fans or heating pumps, for example. Because they're so common and often in use continuously, motors can contribute a significant portion of a site's overall electricity consumption. Unlike other equipment such as lighting and heating, how they use energy is not particularly straightforward though. Usually, however, a little understanding of how motors work and how they perform in different situations can go a long way to managing their energy use. There are several main types of electric motor, but because they're by far the most common, in this video we're going to focus on the three-phase AC induction motor. These motors come in a large range of designs and outputs, but one key aspect is that for any given motor they have a single nominal speed that's dictated by their design and the frequency of the alternating current, or AC, that supplies them. Let's take a quick look at the basics of how they work. An AC induction motor uses a metal outer ring called a stator. This doesn't move but holds coils of wire that are supplied by each of the three phases in sequence. Depending on the type of motor, these three coils will repeat around the stator a number of times. So in this example, the motor has two sets of coils or poles for each of the three phases. When current flows in each coil, it creates a magnetic field. And as each of the three phases energizes the coils in turn, the whole stator in effect has a magnetic field that rotates. The moving part of the motor is called the rotor. The alternating current in the stator induces a current in the rotor's conductors and a subsequent magnetic field, which opposes the one created in the stator coils. As the three phases from the power supply alternate in turn, they push the rotor around one after the other, causing the rotor to keep turning round and round as long as power is supplied. This means that the frequency of the alternating current dictates how quickly the rotor turns. The more times the three phases are repeated around the stator, however, the slower the rotational speed. More poles do, however, result in a greater force or torque from the motor. Motors like this are therefore always described in terms of their number of poles, along with their number of rotations per minute, or RPM, for a given frequency of electrical supply, as well as their power output. Motors of this type actually have multiple poles in the rotor that can be made from coils of wire, similar to the stator. More commonly though, the conductors are made from solid aluminium bars rather than wire coils, which gives them a distinctive appearance that's led them to being called squirrel cage motors. A motor of this type will have a rated output measured in kilowatts, which is related to the torque they deliver from the rotor and their rotational speed. For a motor to operate at their highest efficiency, they should therefore be matched to a task or load that requires this level of power. Because motors have to push against this load, their rotors turn a little slower than the stator's magnetic field. This difference in the rates of rotation is called slip, and it means the rated speed of a motor will always be lower than the synchronous speed of the stator. Motors that have no work to do will still consume some energy, however, and motors that have too much work to do end up with too much slip, meaning that they can ultimately stall. So motors are generally at their most efficient when they operate at their nominal load. A motor that's not matched well to its load can therefore waste energy. AC induction motors draw a high current when they're forced to rotate too slowly. This also means that they draw a high current at the moment they're switched on until they get up to their rated speed. This high current can cause significant heating in the motors, which over time wears them out. For this reason, the more often motors have to start up, the shorter their lifespan tends to be. Most motors state the maximum number of starts per hour that they should be subjected to, and this tends to be lower with larger motors because they have greater heating. This limitation means that even if there is only an intermittent need for a motor, they may have to be run almost continuously just to avoid them starting and stopping too often. To avoid this problem, a device called a soft starter can be installed which limits the current available to a motor when their speed is low. This can have a few benefits, including increasing the lifespan of motors and preventing excessive current being drawn from power supplies. In addition, it can enable motors to be used more intermittently, which may lead to significant energy savings for an organisation. Beyond simply switching a motor on or off in line with demand, it would be much more useful if we could actually vary its speed. Processes could be run more precisely and energy consumption would be only as high as necessary at any point in time. Such a function is possible with a device called a variable speed drive, or VSD. These work by electronically manipulating the frequency of the power supplied to the motor. As we saw before, a motor's speed is directly related to the frequency of the AC. A VSD intercepts the power supply and converts it to a higher or lower frequency to change the motor's speed according to demand. The greatest energy savings from VSDs tend to be when they're used to vary the speed of pumps and fans. And this is because there's often a need to continuously vary the flow of air or liquid, and reducing this flow rate whenever possible can lead to particularly large energy savings. As they have to do work against the drag caused by the liquid or air, the power required by a pump or a fan increases with the cube of its speed. So, for example, if a fan motor speed was reduced by 20%, it doesn't simply reduce power consumption by the same proportion, it actually reduces it by almost 50% of its full speed power. To achieve energy savings like this, VSDs need something to constantly tell them what speed to run at, so some kind of sensor is normally needed to create a closed control loop. In a commercial kitchen, for example, an extraction fan could have its speed controlled by a VSD, which takes readings from a CO2 monitor. As the CO2 level in the kitchen increases, it would instruct the VSD to increase the fan speed until the CO2 level returns to an acceptable level. Without this control, the fan would have to run at full speed all of the time to keep CO2 levels down, potentially wasting large amounts of energy. It's not always economical to invest in a VSD for a small motor. Where this is the case, changing the type of motor itself may be the best option. Electronically commutated motors, or ECMs, basically convert the AC supply to DC, and from there they work in the same way as a brushless DC motor of the type found in modern power tools. This allows their speed to be varied electronically rather than being dictated by the frequency of the power supply. Another type of motor, called a permanent magnet AC motor, may be useful where very precise speed or torque control is needed. They use powerful magnets in the rotor rather than the coils found in induction motors. The power in the stator coils is then electronically controlled to ensure it synchronises with the rotation of these magnets. These can be very efficient motors, but their precise engineering and the rare earth metals used for the magnets can make them expensive. The design of AC induction motors has steadily improved over the years, primarily to improve their energy efficiency. To enable consumers to identify how efficient a motor may be, they are now given one of several distinct energy efficiency class designations. Since January 2017, all new motors with outputs between 0.75 and 375 kilowatts that are supplied in the EU have to meet or exceed energy efficiency class IE3. This also applies in the UK despite its departure from the EU. Regardless of these regulations, it's worth checking the energy efficiency class of any motors being procured, as it can have a major effect on energy consumption. Even a modest improvement in efficiency from one motor to another could give rise to very significant savings accumulating over time, particularly as many motors run continuously day in, day out. Motors that are due for replacement within the next few years may be worth replacing sooner if there is the potential to improve their efficiency at the same time. Motors should be reviewed well in advance of their anticipated end of service to work out if or when an efficiency upgrade would be worth doing in terms of the capital cost versus the kilowatt hours it might save. For this reason, a site with a large number of motors should keep a register of them and track both their maintenance records as well as their predicted and measured energy consumption. It's possible to implement an energy monitoring system for individual motors or groups of motors and observe how consumption changes over time compared to the number of hours they've been running. Changes in their consumption could indicate that they're underperforming and are in need of maintenance or replacement. It's also worth checking the operating temperature of some motors. Any motor showing a high temperature may indicate that it's working too hard or in need of maintenance, and also running inefficiently. An easy way to check temperatures is with a thermal camera, where anything unusually hot is very clear to see, especially when two or more similar devices are running side by side. So I hope you found this video useful. You can find out lots more information about industrial motors by downloading our fact sheet. Or if you're interested in any other technologies, we have a number of other videos available. Thanks very much for watching.